Today's goal is to solve linear quadratic systems of equations. Let's break down the aim a little bit. A system of equations is a group or a set of functions that are all on one graph. And when we say they're linear quadratic, we mean that one of them is a line and one of them is quadratic. It looks like a parabola. And when we're talking about solve, there's a subtle difference we should point out. When you're solving one equation, your answer is called the solution. It produces a solution, and a solution is a single value that you can substitute into the variable to make the equation true. When you're solving a system of equations, we still call the answer or the result a solution, but this time the solution is not a single value. The solution is a coordinate pair. It's an x and a y value. It's a place where the functions intersect. So we're using these words solve and solution in different ways, depending if you're solving one equation or if you're solving a system of equations. Okay, let's get started. First, name the solutions to the systems below. Well, graphically, we know a solution is a point where the functions intersect. So this example is easy. It has two solutions. One is at -3, 4, and the other is at 1, 0, these points of intersection. This graph to the right appears to have no solutions or no points where the functions intersect. The graph all the way on the left, it looks like there's a solution right here at about the point 3, 4. So you can see when we're solving linear quadratic systems or systems where you have one line and one parabola, there are a variety of numbers of solutions, points of intersections, that are possible. Let's take a look at our next example. Now we can certainly solve by graphing, but graphing by hand is a little bit messy and hard to tell where they intersect. You can definitely graph with your calculator and look for the intersection, but you should also be able to solve these algebraically. We're going to use the same strategy we used in Algebra 1, which is substitution. This second equation has y isolated or alone, so we can simply substitute the expression 2x plus 1 in for y in the first equation. So notice in pink, I'm just bringing down everything in the first equation. In black, we just substituted that expression for y. Now you have one single equation with one single variable. There are no y's anymore, only x's. So this is a quadratic equation, which you know how to solve. We'll just combine like terms, get everything on one side of the equal sign. We'll have to subtract the 2x. We'll have to add the 6. Now this is an equation that factors nicely. And when we set the factors individually equal to 0, we get two x values, 6 and 1. But remember, a solution to this system is a point of intersection. You need x values and you need their corresponding y values. So an easy place to substitute would be back into this equation here, although you can substitute these x values into either equation. So we'll say the y value that goes with the x value 6 is equal to 2 times 6 plus 1, or 13. So that produces the solution, the x value 6, y value 13. And the y value where x is 1 is 2 times 1 plus 1. Again, I'm just substituting into the second original equation. I get 3. So I have the coordinate pair 1, 3. So these are my two solutions, the 2 points where these two functions will intersect. One more example. Are there any solutions to this system? So I don't know, let's try solving it and see what happens. Here they're both set equal to y, so I can just set them equal to each other. Or you can think about it as substituting for one of the y's with the other expression. Again, now I have a quadratic equation. There are only x's, no y's. So let's move all the terms to one side of the equation. I try to factor. I want two numbers that multiply to 10, add up to 6. No, that won't work. Okay, if factoring doesn't work, I'll have to use the quadratic formula. Order of operations tells me I need to do the exponents and the multiplication first. I'm just going to bring down that minus sign in between them. Now, for our purposes here, we can actually stop at this point. The question didn't ask us to name the solutions, they just asked, are there any solutions? Because I'm getting an imaginary value for the x value, and we can't plot imaginary points, we can conclude at this point, no, there are not any solutions to this system of equations. This would be a scenario like we saw at the top, like this one, where the quadratic function and the line, they just never intersect. So there simply aren't any solutions. Now, for your own benefit, you know you could simplify this value. This would be x equals -6/2 plus or minus square root of 4 times the square root of -1/2. That's x equals -3 plus or minus 2i/2, or -3 plus or minus I. But again, you're getting a complex value for x, which you can't actually plot. So in this case, there are no solutions to this system of equations.